Okay, well, why don't I go ahead and introduce you, and we'll have you go first, and then I'll just manage the interactions with KWAI here, and we'll do him after that. So we've got two good speakers for our May ECSS Symposium. First, I want to introduce Amit Chirazia from the San Diego Supercomputer Center. So Amit's worked on a lot of different ECSS projects, and the one he's going to talk today about is visualizing time series earthquake data. And this is with PIs Tom Jordan out of USC and Yifeng Hui here at SDSC. Amit's a visualization expert. He's done a lot of different training for ECSS and for other groups, and worked on an awful lot of different projects. So we really are interested to hear what Amit has to say about the experience with the earthquake data. So why don't you go ahead and share again here, Amit. Yep.
All right, great.
Take it away, thank you.
All right, thanks, Nancy.
Oh yeah, questions, type questions into chat would be fine. If you want to break in during the talk, I imagine that's fine with the Amit as well. So we'll try to keep folks muted during the presentation. Yeah, and I'll manage chat and send questions to Amit.
Okay, perfect. All right. Well, thanks, Nancy, for the introduction. Just a minor correction to the work which Nancy mentioned. This work is in collaboration with Jim Dietrich and Keith Richard Dinger, not Tom Jordan. So this is a different project. And Yifeng is also the PI for this project. So this project is about exploring time series earthquake data. So this is the research motivation for this work, is for calculating earthquake hazards. And to calculate earthquake hazard, you require a large number of quakes at different scales in magnitude, space, and time. And the problem we have is we don't really have good records of earthquake. I mean, we have some records, but not sufficient enough so that we can do a good job at estimating the hazard. And this is especially true in the earthquake hazard is quite a big deal in seismically sensitive zone around the world, and a lot of big cities are actually located in those zones around the world. So one way to tackle this problem is to develop synthetic methods to create a large catalog of earthquake which can fill this missing data, and that could be fed into the hazard estimation for creating risk profiles associated with different regions. And so RSQSim is one simulator which generates these kind of earthquake catalog at different scales in magnitude, in space, and time. And so this this code runs on fairly large number of cores, and it simulates a lot of earthquakes, does wave propagation, and reports their characteristics into an output. So currently the code runs on about 1,000 cores, but there is a need to kind of expand it to run on larger number of elements. Currently it only runs on 100,000 elements, but the goal is to kind of scale it further to 1 million elements. And the memory footprint for this code is quite large because it basically calculates wave propagation for every event and calculates which other segments will get affected. And so the memory kind of increases as a square of the number of elements which are to be investigated. The scaling and optimization work for this particular project is being done by Dmitry Pekurovsky, also at SDSC. However, I'm going to focus only on visualization aspect of this work for this purpose of this talk. So let's take a quick look at what the output data looks like. So the output data consists of broadly 3 classes of things. The first one is the event itself. which has, a number of variables associated with it: the time of the event, the magnitude of the event, the location of the event, and so on and so forth. Then there is the fault geometry, which basically describes the faults which are actually used as input to the model, where those faults are located and their subsection. And the faults are actually divided into patches. The patches are either triangular or rectangular, and several of them form fault subsections, and several subsections form the fault sections. And then associated with that, and this is what the simulator does, it creates an event, and then it basically records that quake characteristic and which patches or fault elements it's going to affect, and which we can say is the event action essentially. And this action is actually recorded and again with number of variables, and these are binary files. So the data is spread over many files, and there is an association about the event with the event action and the fault geometry. So all these things are interconnected. However, the data is stored in disparate files. So if you look at a sample data catalog, I'm not going to go through the columns, but basically it tells you, we are looking at a catalog which has about 6 million events, and it used about 250,000 fault patches, and you have about 20 million event actions due to 6 million events essentially, right? And the duration for this particular catalog is 40,000 years. So from 50,000 years passed from the current till about 90,000 years earlier. So the first thing I did was I tried to look at the data, what the data looks like, very, very basic exploration of the event data, just the chronology of the event, how many events happen per year, what is the maximum magnitude which we can see in any year, and at what frequency different quakes happen. So if you just do a scatter plot, this is what it looks like. So here the red quakes are basically the 7.2 and above, and so on and so forth. And we can see that, about, no more than 500 events happen. So y-axis is the frequency, and x-axis is the time scale in years. So starting from 40,000 years going back to about 80,000 years here. And we can see the distribution of quakes at different scales. Same information, we can kind of, switch the axes, retain the x-axis as time, but switch the y-axis to maximum magnitude. And then now we bin things by frequency with color. And so now we can see, how many quakes of different magnitudes are happening with what frequency. So we can see a large number of earthquakes are actually at the, smaller magnitude scale. And again, we can do the same plot in yet another way. Here we are coloring things by year, and then switch the axes. So I'm not going to go through this detail, but the key thing to remember here with this plot is we can see that about 500 events happen, more or less, at the maximum in any given year. Most of the times it's less than 300. So when we started the project, the scientist already had a custom application written in R, which could do 3D visualization. However, it didn't have the geographic context. It would just plot things, as rectangle or triangle, and then and the scientist can see what may be happening, but the geographic context was missing. Also, it's a single user application. And so after having an initial conversation with the scientists, we thought it would be a good idea to kind of create a 2D visualization with richer geographic context and ideally usable from a web browser. So this is what we discussed that we are going to do for the ECRT project. And so the first challenge which we had to deal with was to kind of handle the data. So the data itself was kind of spread around many files, the indexes were some were 0 based and others were 1 based, so they need to be normalized. Again, the variable names across files kind of were the same things but with different names. And then since we were focusing on 3D, but the data, underlying data itself was 3D, that data needed to be translated to 2D. One would think this would be pretty simple, but it turned out that was not the case. The triangles patches were stored in with vertex and 3D rotations. So they could simply not be projected just like that. You have to kind of, do the transforms in all axes to get the right coordinates and then project them. And the rectangle patches were stored in bit different format, which meant that the rectangular patches were stored with the origin, the length and width, and the 3D rotation. So the elements are stored differently for both kinds of things. And then finally, the projections which the scientists use for simulation is UTM, which is mostly Cartesian projection. But when we go and want to display things in a rich geographic context, you have to choose another projection. And one of the most popular one is EPSG 4236, which is sometimes also called web projection, web geomercator projection, sometimes also called Google geo projection. So one idea was to figure out whether I'm going to use the raw data or transform this data into the database. So that was something to kind of look at as well. On the visualization side, the questions came about what were you going to display and how are you going to display? Which medium would work well? Because we have a large catalog, 6 million events. If you show all of them together, you won't be able to see much and not make much sense out of it. And then, so how do you display those many events? And what would be the metaphor, visual metaphor? Are you going to use a map, or you're going to use some different kind of abstract plots like scatter plot and some other things to kind of represent the data visually? And finally, we thought that we may want to make this work on a web browser. Whatever technique we choose, will it work in a web browser? So we started to kind of look at the goal for the visualization was to support geographic exploration. So the idea would be show an event and then show which faults are affected by that event, or which patches in this case are affected by an event, and then have it interactive. And so the implementation for this ended up being with Python, JavaScript, and HTML with assortment of libraries. So in the first phase, I ended up building the application with raw data. It's a lot of data wrangling required, moving the data from one format to another. Also, the data which was given actually switched format, because earlier it was only ASCII data when I started working with the project. And midstream, when I started kind of playing around with the data, they switched part of the data to binary format, because the data, the file sizes were growing with larger number of events they were kind of simulating for different catalogs. And then they also added rectangular patches. Earlier things were mostly triangular. So once we got that squared away, we had a basic application going. The issue was it would take a large amount of time to get started, about 20 minutes, because you'd read all this data and create data structures internally from this entire data set for doing appropriate lookups to display the event of selection. One way to kind of lower the startup time was to pickle the data and save it back to the disk with the data structures which were going to be used by the application, and which brought the time to about 2 minutes. So not bad, but not very convenient either. And then the application was using a lot of memory, because everything was stored in memory. And while the catalog which I was working with was okay to work with, the memory which I had on the desktop, but larger catalogs are planned for this simulation. So the application had to be kind of developed in such a way that it will work with future data sets. Again, this all meant a lot of painful development and debugging because had to wait for the data to load and so on and so forth. So phase 2 was, once I got something working with the raw data, was to transform the data into a database. The question was which database to use, what kind of database schema was to be used. And at the same time, I had very, very little experience with databases. So this was kind of a learning exercise for me to figure out how to choose the database. So in this case, there were some interesting aspects of the data. The data is mostly written once and never changed. And so it's basically a read-only data once it's written. And then it's mostly going to be used by one or more person, but so the concurrent read requirements are going to be there, but we don't envision any concurrent writes. And the other idea was that any database would work, but the question was which one to pick. If we pick any of the standard databases like MySQL or Postgres, basically it requires some setup, and you need a database server, which means the scientists need to run something like that every time or perpetually to kind of work with their data sets. And that seemed like a overkill for this particular project. So I actually explored SQLite, which is a database which lives in a file and doesn't require any special setup. So a file which acts like a database, and it has some nice properties about, it scales fairly well. It's usually meant for a single application, but in this case, there is going to be no write. So it can have multiple users and it'll just work fine. And it also kind of collates everything into one file. So, your data will just still live in one file, which is a binary file. It provides all the SQL-like querying capabilities, and it's heavily used everywhere, actually. In your phones, most of the applications are using SQLite to store their data. And one good use for SQLite data, which the project actually, the SQLite project actually mentions, is to use SQLite where you have kind of homegrown formats. So instead of writing ASCII or your data formats in tribal formats, SQLite is a good container for those sort of things. So which kind of meet the bill for this sort of project. So we ended up picking SQLite database as the database of choice. And then the idea was to switch the application to use the database instead of the raw data, which meant taking away large parts of the code and throwing it away, and then transform all the lookup and searches into queries. However, I soon uncovered that the query performance was quite slow. And being a recent kind of learner for databases, I was not very familiar with creating indexes and things like that. So I delved into that and created indexes for the kind of queries I was doing. And that boosted the performance, about 2 to 3x. And that was quite good for a web application, because we want the round trip times to be fairly quick. When the user interacts, you need to ideally respond in less than 2 seconds. Of course, this is a scientific project, and if it takes longer than that, it's okay. But for general querying, the shorter the turnaround time you can offer, the better it is. Another challenge with this kind of data would be kind of selecting the event. We kind of formed the visualization about event selection. So you are going to select an event and we're going to display it on a map. Now the issue is that we have in the sample catalog which I'm working with has 6 million events. How do you choose an event in that? Well, one idea is to create a slider, right? You can quickly just scrub the slider and and create and pick an event. Or you could type a ID for an event. So you got about 150 pixels to pick 6 million events, and then otherwise you type a number or ID to kind of choose an event. And so this was not really a good idea. So one idea was to kind of what can we do to kind of make this a little bit more easier for the users to kind of not having to type, but still have some crude capability to kind of select events in somewhat better way. So what I ended up doing was creating additional kind of buttons to increment or decrement the events by a different scale. So by 10,000 or 100,000. So skip every other order of magnitude, or every 100 times order of magnitude, and make them available. So while this was nice, a better thing was to actually provide all orders of magnitudes which a person can select and lazily skip and choose events if they were not interested in typing. And this is probably more meaningful if you're going to be using a mobile device to browse something, where scrubbing a slide or selecting something would be a little bit easier than typing exact numbers, unless you know what you're looking for. The same thing needs to be done for time. The time here is actually recorded in seconds. So you have 40,000 years, but the granularity is seconds. So you need to kind of give the event time in seconds and then figure out whether an event happened at that particular second. If not, snap to the closest event which happened in the time which a user has chosen. Again, displaying the map alone may not be sufficient. So the idea would be to show adjacent event to the selected event, maybe as a time series. And so once I show you the representation, you'll have a better understanding of what I'm talking about. And then, of course, the UI needs to be mobile friendly. So here is a quick kind of overview of a visualization design, which went into the development of application. And so here we have a geographic context, and then this red mark basically represents the selected event. And then we have the number of patches shown in blue, which are affected by this particular event. If you zoom in, you can see these are triangular or rectangular events in 3 dimensions, but they are projected onto 2D, so they can have weird shapes. And then you have kind of add further a few more events to kind of show the chronology, because showing one event may not be sufficient. It might be a good idea to show events on either side of that event, that which events preceded that and which events are going to follow. So the black events here, or the black markers, show the events which have happened before, and the purple events are the events which are going to happen after this particular event, which is shown in red. Now, if we draw a line, that basically gives us the chronology for this event. So we can trace the line and see which events happened first, and then get an idea of how the events are related to each other. And then, of course, you have all these layers which you can turn on and off to show different aspects. If you don't want to see certain thing, you can turn that on and off. And then here is the time series which I was referring to. And in this particular case, this is the event which the user chose. And now we are displaying 100 events before it and 100 events after it. So we are showing the magnitude, the time duration of the event, how much area they affected, and that's displayed here. And these things are interconnected. So if I click a point here, let's say here, it's going to go and update the map and show this particular event in the map. Okay. So the interaction basically allows the user to select an event by ID or by time. They can filter these events by magnitude. Let's say you're only interested in seeing events which are at magnitude 5 or above, or they affect maybe 1,000 patches or more. or maybe you want to see more trail events on the map, you can customize those things. I already showed you a reference to layers. You can turn them on and off. Also, the markers which show up on the map, if you click on them, they pop up and give you information about what other details are associated with those markers. And then finally, the time series is linked with the map. If you click on any point on the time series, it basically updates the map. And there is also a notion of enabling constraints. So if you're going to set some filters and say that only show me the magnitude, the events between certain magnitude and certain number of patches, you can actually filter them and apply them to the time series also. Excuse me. So in this particular case, not only you see the events which are just adjacent, but you can also see the events based on filters which you apply. So let's take a quick look at the interactive demonstration. You can try it yourself if you're interested. Excuse me. So this is the application. You can see different layers. There's just one map style available. Pardon me. We can turn off, the selected event or the patches or the trail events or the lines which connect the event. So let me give you an example of the pop-up here. So if I click on the selected event, I can see different attributes associated with the selected event. Now let's go ahead and select any other event. So we can do it via slider, or we can, march on using these different kind of schemes which we have, and then submit it, and then we get that new event which we just selected displayed in the context. We can zoom out a little bit and see some events surrounding it. We can see, there are events all over the place. So very likely the adjacent events are not really related to this particular event. But in some cases, the scientists are interested in seeing if the earthquake kind of hops from one fault to another fault system. So in that case, you can see some interesting kind of correspondence between preceding and following quakes. You can actually set up different kind of filters and say, hey, we want to see quakes between certain number of magnitudes, and maybe it affects some number of patches. You can say one way or the other and submit, and it's going to query and figure out that and find that event. Now notice in this particular case, when we are setting the constraints, we may not find an event at the chosen ID. In that case, we will find the application finds the nearest event around the chosen time or ID and displays it, because now we have set constraints. Excuse me. And there may not be any event available in a catalog at that precise ID. Excuse me. Again, you can select the event based on time. So now here we can see the years, days, hours, and seconds. A similar notion of granularity is available to select event based on, a different granularity without actually having to type the number of seconds. You can notice that, the number of seconds here is, 13 digits. That could be quite tedious to kind of figure out and type. So event ID may be a better way to kind of look at, unless you know exact time you're interested in kind of exploring. And then there are a few other features like, fit things automatically, so you don't have to kind of zoom things in and out. And by default, this auto applies on because you may probably want to get things set up before you, otherwise it fires up every click. So those things are available. And then here is the timeline. So the event at the center is the selected event, and then we are seeing 100 events before this and 100 events after this. You can toggle different things here and see them. We can also zoom them and see what may be happening and kind of, look at that in more in detail if we have an interest in doing so. And then we can also decrease the number of events we want to see on the timeline. By default, we show 100 events, but we can increase or decrease the number of events we are interested in seeing. So I'm going to do auto apply here, maybe show more events, and then we can get more events or less events depending on what's there is of interest to us. And similarly, you can show more events on the map itself. By default, we just show 5 events preceding and 5 following. But if there is an interest, you can increase the number of events which needs to be shown on the map. The reason we chose low number of events is it ends up cluttering the map very, very quickly. So it's really hard to see what may be going on. Okay, I think I have auto apply on. That's why you don't want this on all the time. All right, so let me zoom in here if I can show this. So if I click on this patch, it's supposed to give me a pop-up because all this information is already baked in and available. However, there is a outstanding bug in the underlying library, so it doesn't display the pop-up like it does for the main events. All these patches, in this case about 7,000 patches, we can get information on each of those by clicking. But that's, for some reason, because of that bug, it's not displaying correctly right now. I also actually ended up implementing a heat map, which would show the heat map of surrounding events. But I ended up finding a bug in one of the popular plugins for Leaflet, which is the mapping scheme I'm using for this project. And so I abandoned that because it was displaying things incorrectly. And so there is an outstanding bug in that stack right now to kind of fix that. Okay, so that's a quick demo. If you're going to try this, it runs on a non-standard port. You just keep that in mind. Once the data was transformed into the database, I thought it would be a good idea to give scientists a feel for doing some analysis with the database backend versus the files backend which they were using. And so we chose an analysis which basically calculates the mean recurrence interval for a fault subsection. So a fault is divided into many sections, and each subsection has a name associated with it. In this particular catalog, there are about 2,600 subsections. And the idea is to figure out what is the recurrence time at which an earthquake happens in this subsection for every subsection in the system. And there are a couple of variations here. The first variation is which says with nucleation only, meaning only find out the intervals when a quake originated in that subsection and was not affected by any other event. And so if we calculate that, it takes about 2,000 seconds. But if we choose to kind of include the participation, which means any of the fault patches were affected by any other event which may not have happened on subsection, the computation actually becomes more complex, and then it takes a little longer, about 13,000 seconds. And so we verified and validated these these calculations with the scientists' code, and they worked fine. So I wrote the code in Python, and the scientists had their R code. And we are still kind of figuring out the timings with the R code. I think the database code is probably slightly faster, even though it doesn't use the data from the memory. It doesn't read the data from memory, just because the database querying is very, very efficient. But we are awaiting further benchmarks with the R code. I don't have the R code, so I couldn't benchmark it. But the scientist is going to benchmark both things on their computer. So conclusion. So we ended up transforming the raw data into a database, which is much more easier to use because it's just one file as opposed to 11 files. It's much more scalable because it doesn't need to be loaded into the memory. The querying is fast and fairly easy. You don't have to write a lot of custom code for doing, fancy querying, which you have to do with custom data structures. More or less, there is good amount of detail available on how to index, how to write queries for basic operation, which is what the scientists need for the most part. I ended up providing them a good deal of documentation also. Okay, there's something here. As project deliverables, I wrote a generic script which would convert the raw data to a SQLite database so that scientists can point to the data folder and it creates a database for them. The web application, which we just saw, is also available to the scientists to use and deploy. And I also provided them the analysis script and some other query examples with which they can start to use the SQL-based database for their analysis, and of course associated documentation. Again, there are some interesting potential for the research team to kind of take this forward. They can translate their analysis code because now it doesn't require any parsing. It's going to lead to less code, meaning less error prone. And then they can directly write their data to SQLite database from simulation instead of writing ASCII and binary files. So they have less data to kind of manage, which is spread across different files. But the downside is they will need to learn how to write SQL queries. So from my perspective, there are assortment of technical things I learned, playing around with databases, playing with different Python and JavaScript libraries, and also playing around with graphical user interfaces. Turns out on the web, things don't work as you think they would. So you need a lot of glue and shins to kind of make them work from desktop to mobile devices and things like that. There are interesting possibilities again for the science team. They can think of converting this to a gateway and offer it as a data service where you can just query and download the data. You can also allow visualizations could be extended to allow spatial filtering and heat maps and things like that. And we have a publication which is upcoming. So this was my practice run for the publication presentation at PERC. And then, of course, the work was funded by the National Science Foundation for Exceed, as well as for the science project, which is funded by the Geoscience Directorate and also by the KWAI Foundation. Well, that's all. Well, if you have any questions or if you have any time, I can take some.
Amit, thanks very much. Great presentation. I'm not going to take too many questions because we're already running late for KWAI's presentation. But Chunhan Yoon comments about the IRIS database for seismology that also includes earthquake and data events. I don't know if you're familiar with.
Actually, I'm not, so I'm going to go talk to Chunhan.
Excellent. Okay, very good. Thank you. Great presentation, and I really like the way you kind of outlined the whole structure of the ECSS activities, from cleaning the data to speeding things up to learning about new technologies and making selections.
Cool.
Yeah, what it did for the science team. So thanks very much. It was a great dry run. We'll look forward to hearing you again at PERC.
All right.
Okay. Thanks a lot, Amit.
All right.
So our second speaker today is KWAI Wong from NICS. So KWAI is on by phone, and I'm going to be driving the slides for KWAI. KWAI was working with PI Matthew DeAngelis from Georgia State University on disclosure scriptability. So basically looking at financial disclosures and text mining to see if you can understand content from large amounts of data. So think the iTunes license agreement, that sort of thing. So happy to have such a diverse set of projects today. Let me go ahead and share my screen, and then KWAI, I'll let you know when we're ready to go here. Okay, great. So we've got your first slide, the title slide on the screen, KWAI. So if you can talk through these and just say next slide, I'll advance them for you. Let's see, I saw you on by phone. Are you muted, KWAI?
Right now, I can.
Okay. We can hear you, KWAI. Can you go ahead?
Great. This is the project that I work with a researcher in the Georgia State University, and he's not a what we call a traditional science person, but he does these kind of document research, and so this is a little bit different from my area, but it's a good try. So I'll try my best to explain some of the work that I've done. Next, please. So I like to show off a UT a little bit. I mean, particularly, of course, you know, this the big football stadium that we have, and that is one of the big games that we have, and you can see all the checkerboards, orange and white, and that's a signature errors hall in here. Of course, the bottom one is the building objects and the National Institute of Computational Sciences. Right. Next, please. So the goal of the ECSS project is to provide support to manage and run a set of computer codes. And in this case, it's a set of Python codes. That the purpose is to examine the scriptability of a large volume of documents. I guess the large volume is important. So overall performance and IOs and some of these things are issues. And particularly the researchers in this case is new to ECSS, and he has been running on his laptop and also a big cluster, a big single box with a lot of memories at the university. And so we're just trying to explore what kind of opportunities that we can do, provided the resources at Exceed. So the documents that they are doing is for trading, is a trading strategies. So they examine some of the documents that are disclosed, and the firms are disclosed. And instead of using the human to read a lot of these things, they try to use the computer to capture a lot of these keywords and some of the unstructured data, and look into it and see what particular things are similar, and what are they trying to do, and in terms of trying to figure out what kind of valuable data it has. So basically, the two basic dimensions that they're trying to measure. The very first one is to identify the data of interest, and then transforming that data into a decision-driven information. So basically, it's a set of composite measures, and they have some kind of similarity measure that they do in the code. But in general, my task is not per se to help them to write a different code. My task is per se to help them to port the code to these new platforms on ECSS, and try to make it, you know, more available, and try to run the workflow for them so they can use the parallel computer to do the work. Okay. Next, please. So this project involves analyzing, categorizing, annotating approximately 12 million regulatory filings from the SEC. That is the intention. So the intention is they do have these big database of 20 terabytes in size, and right now this is their project. The research project is how can they try to scale the operation up to manage to analyze all these files. So the data is organized in a daily compressed files. They are tar and gzip file, and so they are by a day. For example, is year is 2005, and is in March, and it's a work day, which is maybe perhaps is March 1st is a work day. And under that tar files, there are a lot of files inside. There are a lot of filings inside. Those are documents, and each document they want to look into it and examine some of these similarities. So there are roughly about 8,000 compressed files for plus or minus, depends on that particular day, for one particular tar file. And each contains several, thousand filings, and the total size of the compressed file is roughly 850 gigabytes. So the flows of the work, it's actually very simple. I mean, the first thing is to unzip the daily file and pass each filing to the files, and then start the Python script. So it's a totally written in Python script. And each script perform a variety of operations, and mainly this compute the variable described in some of these particular attachment that they send it to me. So they have a specific fixed things that they want to do and see what kind of things is in there. And then they collect the output from the scripts and write it to a series of CSV files. And some of the outputs that's collected in one large CSV file, and then they will pass it to the second stage. So the first stage is really just doing some of the processing, and it's a lot of memory. They require a lot of memory to do it, but it's not per se a lot of computing. The second stage is to construct the word vectors and output for the first stage and construct a distance measure. Mainly is doing what we call cosine similarities operation. All right, next please. So as I mentioned, the code is written in Python. It's technically just what we call it, a single code. There are many modules in Python. And it achieves parallelism based on multi-processing package in Python. So you can only, for that particular code, you can only work within a node. That means you cannot go outside at this point. So the project started a little bit late, and they start up in January, but they don't have the code ready by that time. So you start up in about, I don't know, in about April, something like that, and they have different versions of the code. And totally there are 4 versions: the version 1, version 2, version 3, and version 9. So they keep on changing it. It is trying to see what kind of performance that they get and what kind of memory requirements they have. And it seems that the final versions, it is very good. And the version 2 of the code is also very good. And I have done a lot of analysis for version 2. Okay. So the second version was tested on Comet and ported to other Exceed platforms. And the third version turned out to be not good, because it seems that they changed something and they require a lot of memory. And since Comet has 128 gigabytes, and same as Comet, a lot of these work will not be finished because the tar file is just too big. So we focus on the second version, and we have some results for the last version. So the beginning, it's a little bit problematic because they use Python 3.5 and they use NumPy and SciPy, and they also require a lot of different packages. Panda, BS2, NLTK, Pen, Python, Enchan, and a lot of these different packages. So it takes a little bit time to figure out and what kind of things that they need and make the codes to work. And particularly, it's difficult is to install the Enchan linking to the dictionary available in RB Word. That's the most difficult part that I spent a few weeks of time trying to figure out what's going on in there. And they seem to put everything in a memory. I mean, particularly also they require about 2 gigabytes of files. It's called corpora. I mean, so these are the data that they need to process or compare, whatever it is. So as I mentioned before, the first day is unzipping, doing some of these things, and they have a methodology of, in the Python code, how can you divide up or decompose the word. So particularly in the Python code, they said, what is the number of processes that you use? It's called pool. And then the pool count and some of these things. And they will divide up into pool count 1, pool count 2, and pool count 1 multiplied pool count 2 will be equal to the number of total process working on the filing. And I will show you some of these things that has been shown. So the last process, basically, once they decompose the work, and each work will basically perform a cosine similarity comparison. As I mentioned, that this is almost an embarrassingly parallel operation. So it's really ideal for if we can fit everything into a computer, then how can we do it? So it's ideal for some of the workflow analysis that I have been doing. So I've been using one of the engine to help them. Okay. Next, please. So this is the workflow for what they have been doing, and basically you can see that. And they start with the untar and assign some of the documents to the processes. And if you look into the second level and the third level, they have a lot of cosine similarities between headings, between subtitles, between any other things. So basically, the major calculation is really a cosine similarity operation. And at the end of it, they put all these together and then send out an output file. Next, please. So this is the data and the performance. So the data is organized in a daily compressed file, and the findings of March 2005 is used as the testing data set. So I got a data set from them, and the data set is listed on the left side of the box. And you can see that the size of these varies a lot. I mean, so in the beginning, in order to make sure that everything runs correctly and tested correctly, I chose 4 files, which are very small. So you can see that is March 03, March 21, 23, and 25. They are fairly small. If you look at the very last one, which is March 31st, it's a humongous file. So there's a lot of low imbalance if we want to do it in parallel in this case. So the first step is to run this code on a single node using different code. So in the program, it set the pool count 1 equal to 4. That's used for unzipping. Pool count 2 equal to 2, used for processing files. And pool count 1 multiplied by pool count 2 will be the total code. And that's how we adjust the how many cores that we use. So I run it on Beacon. Beacon is our machine. Beacon has a very large amount of memory. It's a 256 gigabyte memory, so it runs pretty well in this code. And the time for it is for this particular case, we use 8 core, and it's 207 minutes to run that 4 files. And then the second box on the right are the results from bridges. So we can see that if we use count 1 equal to 4, count 2 equal to 2, 8 cores, we use 165 minutes. And then if I use 12 core, 135 minutes, and 16 core, 95 minutes. Although the scaling is not perfect, but in the case that in this particular case, we can see that we have speed up in this particular case. So typically, if we use 16 cores, and then if the memory fit into everything, and we should be fine. So I also run on Comet, and Comet, this is a different version. This is version, well, this is version 2, still version 2. But for Comet, I fit everything within a node using 24 cores. And you can see that it's 4,100 seconds. That's about 67 minutes. So if we compare the result to the 12 cores in Bridges, so it's about right. So Bridges is 1/4 minutes, and when we multiply 67 by 2, that's almost 135 minutes. So we can recover some of the performance. Okay, on Bridges and on Comet, they are very comparable. They're very good. So I also try to put it to Stampede, but this won't run on Stampede core because each Stampede node has only 32 GB of memory. So it just won't run. That's it. Next, please. So the next step is to use a workflow engine, try to run everything together on a large scale. So I'm sure I have talked about this OpenDIEL, and this OpenDIEL is a workflow engine. The good thing is it's launch it launches everything using a single MPI communicator, and so it has some communication layers that you can use. And what we can do is to fit everything in this what we call OpenDIEL runtime engine, and then launch the job. Next, please.
We've got a quick question, if you don't mind an interruption here.
Sure.
Someone comments that on Bridges there are 28 cores per node, and they were wondering why 12 were used for this.
Right, usually up to 16, right.
I guess Sudacar is reporting that there's 28 core nodes on Bridges.
I only run it up to 16.
Okay, I think they were talking about the comparison on Comet where you ran on 24 cores compared to Bridges where you ran on 12.
Yes. I did not run it on 24 cores. Somehow there was some problem with getting the code successfully run on 24 cores on Bridges.
Okay.
And the text in here is that somehow the version of Python is a little bit different, and some of the memory requirements are a little bit different. So particularly on Bridges, they use the Intel Python. And Comet, we use a regular Python. So there's a little bit different between the Python, and I could not get it to run on 24 cores.
Okay, thanks for the answer. We have just a couple of minutes left here. We can go a little bit over, but not too much.
Right. So we just basically the next slide, please.
Let's see. So I was on OpenDeal with the flow chart.
I'm done with the slide, right?
Okay,
The picture.
super. There you go.
So this is just a general description. It's a very small, compact code, and the good thing is we can put any serial and parallel code, combination of code together and run it. Okay, so it's nothing very particular. If there's any interest, we can talk a little bit more. But the only thing different is run on a single MPI executable, very similar to a SCRIPT. Next, please. So the key point in here is all we have is need a what we call a configuration file. The configuration file is listed on the right. That means all we need is just put the function and put the data and how many copy of that particular executable you want to run. So for serial code, the user don't have to do anything. All they need is just give me the configuration file and they can run it. So I'll show you how to run this thing. Next slide, please. So this is a serial code. So all they need is the top piece. That's what the user input file. And the input file form is like that. The function is module 0. And that's the code. And that's the name of the code. And then what do we run? We just run Python 3. And then the code that run is main process script version 2.python. that's exactly how they run it if they run it serially, or that's just launching one single node job. And then the code will split up all the directory. So for example, we say size 8, that means it will use 8 node to run it. There will be 8 copies of this process run. Each copy will launch on one single node. And the bottom one show how we run the things, right? So in this case, the bottom one is the PBS scripts, the batch script for the running on Comet. So the node is 4, and all we need is just the IB run is there's m per node 1, and then driver AM, and the workflow files, which was the one above it. That's it. That's the workflow input file. And driver AM, it is a pre-built executable that they don't need to do anything, or they just call it. For serial call, all they need is call it, whatever copy they want to run, and that will be it. Next, please. So that's the data. So for on Comet, for one node, 24 cores, 4 tar files. The tar files was the previous one that they've seen. So we can see the speed up in here. So of course, for one node, we have only processed 0, so it's 2500 seconds. For 2 nodes, we spread it out, so with 2 tar files on each node, and it goes down to 1300. And for 4 nodes, then 96 core and 1 tar files on 1 node. And we can see that it's about 700. And there's low imbalance in there because the size of the files is different. So we can see that for 4 processes, the earliest they're finished is process 3. The time is 594 seconds. And the last time they come out is process 0, is 757 seconds. So OpenDIO will split out all these timing for you, will tell you which one is the best, which one is the worst. So we continue to work on these things. Next slide, please. So this time I changed the files a little bit. So we picked up 4 different files this time. 6 different, 2, 3, 4, 5, 6, 7 files this time. And the sizes varies a little bit. So the first, we use one process is about 10,000 seconds. And then we use 2 nodes, well, 2 processes. The load balance, in fact, is pretty good because we have many files that we can mix and match and then balance it. So we put the large file together with the small files, and then in that case, because we have many files, we can balance it a little bit better. So we can see that the discrepancy is about 4,900 to 4,800. It's not that bad. But if we run 3 nodes, and because of the displacement of the size of these files, we actually got a big difference in load imbalance. 3,000 seconds to 1,700 seconds. So far, that's what we got. Okay, next please. So this is just for future reference that you can mix and match all kind of schedule for the OpenDIEL, or you need just described it. Since we're running out of time, so I'm probably just through the next few slides. Next, please. So we are building a GUI, and it's coming soon. Next, please. So that will be the last slide. So for questions.
Great, thank you very much, KWAI. Let's see, we've got one coming in on chat. Just sort of a comment about distributing the tar.gz files on different nodes, changing the memory requirements.
Yes. Is it a question or is it?
I don't know. Okay, yeah, let's see. Yeah, go ahead and unmute. Yep.
Can you hear me?
Yep. Go ahead, Sudhakar.
Okay, yeah, just if you so if you distribute them, would the memory be less because it is just handling only one tar file instead of all the things in one node, or is there any, or there's no advantage?
So the code has a fixed amount of memories because it loads all the tar files in there, and also it has a lot of other data that it load to it and compare to it. And
so you're saying that all the tar files are loaded in all nodes?
it is distributed. It should be just loaded on the distributed node. But somehow, when the code seems to have some problems, when the code seems to have a lot of files loading together, they have a tendency that it runs out of memory. So far, we managed to do a lot of the work with that particular month. Will be fine. I mean, for the on comment and bridges.
Okay.
There was one final question that came in, KWAI, from Alan Craig, asking if these tools would be useful for other text collections besides the Edgar database.
That I cannot answer because that is their research project. But the way I see it should be. I mean, because they are just looking in some of the files and some of the keywords, and I guess. The best person to answer it is the PI.
Okay, so do you think, because Alan it works in digital humanities in ECSS, and so probably text analytics for reasons other than financial disclosures. So I can see why he's interested. So do you think the PI, do you think Matthew DeAngelis would be open to a query from Alan about the utility of this for other applications?
I believe so. I mean, he is pretty nice and very forthcoming of a lot of the things.
Okay.
And
great.
also a lot of these the work. I hope the OpenDIEL can be helpful also, because if those jobs are very serial and multiple serial jobs, they really don't have to do anything. And rebalancing the work can be done using a Python script, and they can run it. In the workflow analysis, they balance it and then collect it and then do some of the work also. So if there is anything that I can help in that category, let me know.
Yeah, thanks. It strikes me that I should connect you with Marlon Pierce, who's looking at workflows across Exceed and works with a lot of the other tools. So yeah, we'll make that connection too. What department was Matthew DeAngelis in? Just curious.
I think it's in accounting. Something like that. It's either business or accounting.
Okay, great.
It's definitely not in the physics hall.
Yeah, very good job switching domains. I think at this point we'll need to end. We're a little bit over. Thank you to everyone for joining this month's symposium. Thank you especially to our speakers who helped me out kind of at the last minute preparing these talks. So really appreciate both of you and your very good presentations today. Thank you very much. Next symposium will be June, and then we'll take a break for July due to the PERC conference. So I think that wraps it up for today. Thank you very much, everybody.